Welcome to the ONAP Introduction module. In this ONAP Introduction module, we will first explain the ETSI NFV orchestration systems and their origins. Then we will define the objectives of the NFV orchestrators and network automation platforms. Later, we will introduce ONAP, or Open Network Automation Platform, including its purpose as well as its scope. At the time of the NFV reference architecture definition, the standardization bodies realized the size of the scope planned for NFV and divided the further work into phases. There have been at least 2 phases planned, and the reality around developments of NFV platforms revised those plans. Phase 1 of the NFV has been decided to focus on the infrastructure-related area and covered hardware-related metadata, virtualization capabilities, high availability of infrastructure to match 99.999% availability, virtualized infrastructure manager (VIM) standardization, where OpenStack has been selected as a de facto standard. Phase 1 was completed in mid-2015. At this time frame, certain initial implementations of reference ETSI NFV MANO stacks were published. Phase 2 of the NFV standardization has been focused on items which would improve the adoption of the NFV technology. At the same time, significant efforts have been spent to further define the NFV management and orchestration NFV MANO stack. Additionally, several companies and organizations proposed and published their open source contributions around MANO. As a portion of ONAP functionality falls into the NFV MANO area, orchestration, VNF, PNF management, network service deployments, this phase of ETSI NFV activities is relevant for further consideration, and at the same time, the standardization bodies started to spend more time on NFV MANO solutions. These activities have been happening with different vendors and organizations who started to propose their own implementations. In the meantime, some initial implementations of reference NFV MANO stacks have been started, supported by different industry players and different operators. A list of most notable implementations is shown on the next slide. After the NFV infrastructure has been stabilized, around 2015, certain NFV MANO platforms have been brought to public by their founders. Initially, there have been 4 different notable platforms in the open source market. OpenMono, founded by Telefonica, covering the NFVO, OpenVIM, and OpenMono GUI functionalities. Open Source Mono, hosted by ETSI as a reference ETSI NFV orchestration implementation. OpenO, hosted by Linux Foundation and contributed by an operator group where a lead has been CMCC. openECOMP, founded by AT&T as an internal project developed as part of the AT&T Domain 2.0 initiative. Each implementation of MonoStack was different, built using different components, operating on different interfaces and packages. These different implementations have been supported as well by different vendors and different operators who effectively showed very poor technological alignments. Models and descriptors defined by ETSI have been implemented using different methods, and it was not possible to use the same application, VNF, with different platforms without metadata changes. At the beginning of 2019, there are 2 competing NFV MANO platforms on the market, Open Source MANO and Open Network Automation Platform, ONAP. Formally, ONAP was formed at the beginning of 2017 by merging the code of 2 open source projects, OpenO and openECOMP. Essentially, ONAP's scope, compared to other NFV MANO platforms on the market, is broader and covers as well network automation aspects, operating in both ETOM CSP operations categories, service fulfillment and service assurance. As we've learned before, openECOMP was created by AT&T in cooperation with a few telecommunications and cloud infrastructure industry players. Let's have a look at what the operator's objectives have first been behind the platform creation. The main goal of a network automation platform is to support the automation of different lifecycle processes. With introduction of cloud NFV concepts into the telco industry, resulting into more flexibility and agility, usually the complexity of customer service setup grows. In such an environment, it is possible to survive without an orchestration system, which automates different lifecycle operations, creation, updates, deletion of services VNFs, leveraging appropriate templates. Cloud NFV environments provide as well certain new capabilities, like on-demand resource availability, which can be used in service assurance. The closed-loop approach supports service assurance by gathering and analyzing the monitoring events and triggering the corrective actions based on predefined policies. This approach reduces the amount of manpower needed to execute repeatable tasks and allows one to refocus on innovation. The operator's customers are looking for the service delivery speed and agility that web companies like Facebook, Amazon, and others in that space can provide. This agility of web companies is assured by a high level of automation, but the most important aspect is the ability to change and adapt. Only a flexible, scalable, and configurable platform with vivid community-based development is able to answer to such a requirement. Now that we know AT&T's objectives for openECOMP, let's have a look at the objectives related to merging openECOMP with OpenO and releasing ONAP. ONAP is already a recognized open source system with a vivid vendor and operator ecosystem around it. The following benefits of going open source are expected. Open source software is expected to become a collaboration platform between vendors and operators. It allows operators to express their needs and system usage scenarios with vendors, and vendors are able to expose their technology details, so the software could be leveraged better in an operator's environment. A really important aspect here is that publishing the code of a platform solution allows different vendors to integrate their software solutions not only with the platform's interfaces, but with platform mechanisms as well. Additionally, the possibility to obtain the code, build a system, and use it for testing allows one to reach better quality of an integrated system compared to proprietary platform software that is not publicly available for use. This allows one to build a next level of vendor-operator relationship where they act as partners, working on a common solution, and to everyone's benefit. An implication of the previous point is a simplification of network service, NS, and virtual network function, VNF, orchestration. One of the common problems in the NFV orchestration industry is the VNF onboarding, which has to be executed for different platforms separately, as those platforms support different onboarding package formats. Open source simplifies these activities, and the specification of a package is publicly available for adoption. It reduces the integration efforts on the vendor and operator sides, because a package can be prepared by a vendor before an integration in the operator's environment happens. Last but not least, with a vivid ecosystem of operators and vendors, the objective becomes to create a de facto standard mono stack. As explained before, a number of different mono solutions exist on a market, open source and proprietary, and in many cases, there is no complete adoption of standards of interfaces, data formats, and mechanisms. The NFV MANO stack industry needs a de facto standard that can be referred to when developing software solutions and creating services based on them. Especially when an open source implementation exists, vendors and operators might use that one in order to provide better aligned VNFs, and use them quicker in customer services by operators. Now, let's explain what ONAP is and what its purpose is. ONAP stands for Open Network Automation Platform. ONAP provides an open-source platform that can be used to automate a range of service management actions, thanks to its open architecture and a model-driven approach. Looking at the ETSI NFV reference architecture, ONAP is an implementation of a management and orchestration MANO stack, extended with service assurance capabilities built on a closed-loop approach. In an eagle's eye view, ONAP covers two areas of functions. On the one hand, design time functions which are related to VNF onboarding, resource, and service modeling design. On the other hand, runtime functions which are related to service deployments in connected cloud instances regions, as well as service operations activities. Essentially, ONAP activities include service design, service deployment, and service operations. The service design activity targets the definition of service models, infrastructure, and customer. Service models serve as templates that can be used to deploy service instances which fulfill service activation requests from customers. Service design allows one to define different services. A few examples provided in the ONAP community are vVolte, vCPE, VFW, and vDNS. The operator is able to model and define additional services needed in his/her environment. These activities are sometimes referred to as day zero operations. As a service model is created, an operator can move on to the next activity. The service deployment or service instantiation activity targets the creation of service instances based on service models, template, defined in the previous step, service design. It is important to mention here that resources, which serve as service building blocks, are deployed in connected cloud NFVI regions, and services can span across multiple cloud regions. In this sense, services are deployed with or using ONAP rather than on ONAP. Service instantiation activities are called day one operations. After a service instance is deployed, an operator can move on to the next activity. The service operations activity targets the 24/7 operations of deployed service instances. It includes gathering the VNF monitoring events, analyzing them, and suggesting service or resource reconfigurations. Service operations also cover detecting faults and reacting on them automatically, for example, by VM evacuations or redeployments of VNFCs. Many of these actions happen through orchestration activities covered in service deployment. It is important to mention that service deployment and service operations activities may bring important feedback to service design. Such a feedback loop is not defined technically in ONAP. Usually, feedback is gathered in deployments in which operating service instances support design improvements. The purpose of ONAP is to provide capabilities needed to automate processes in service fulfillment, as well as service assurance areas. In the scope of service fulfillment, the following areas could be distinguished: network service orchestration, customer service orchestration. In the scope of service assurance, the purpose of ONAP is to automate repeating activities in network operations. Let's have a closer look at certain examples in the fulfillment and assurance areas. Within the service fulfillment area, ONAP supports automation of network service orchestration, as well as customer service orchestration. Network services are basic infrastructure services that provide essential connectivity capabilities which can be used in customer services. Customer services define the end-user service capabilities and properties. Let's have a look at an example of a vCPE service, one of the services supported by ONAP today. The network service model defines a topology of virtualized network functions, like VBNG, VGMUX, VDNS, and VDHCP. This topology serves as an infrastructure that can be used by the customer service, which defines different capabilities like upload-download speeds, latency, or parental control rules. When a customer service is instantiated as part of a customer service fulfillment request, there is an attempt made to locate or instantiate, if not found, an infrastructure service available. The deployment of a customer service might require the deployment or modification of a network service which supports that customer service. In the case of this particular service, a service activation relates to registration of BRG devices. For each of these devices, a virtualized function corresponding to each device is instantiated as part of a customer service instantiation. Additionally, in the scope of the customer service instantiation activities, a tunnel is created between these physical devices and virtualized functions, which, in practice, corresponds to a configuration change on the relevant functions. This way, ONAP is able to automate the network service deployment and modifications, as well as customer service instantiation, even if such an action requires topology and/or configuration changes of an existing network service. Service fulfillment automation with ONAP is based on several capabilities. First of all, the services need to be designed. ONAP supports service design operations using the TOSCA approach. Essentially, designing a service with ONAP covers VNF onboarding, resource creation based on VNF packages, and finally, service design based on resources onboarded in the previous step. A graphical design tool called Service Design and Creation, SDC, is available to execute design operations. SDC capabilities will be introduced later in detail. After the service is designed and distributed, announced to all ONAP components, a service orchestration picks up the service deployment. Within service orchestration, different activities are executed. A service decomposition is required to evaluate what the VNFs to be deployed exactly are and what the right sequence of orchestration steps is. Another activity is the selection of a valid cloud region. A large number of cloud instances regions could be integrated with a running ONAP instance. ONAP comes with a framework, which allows one to select an optimal cloud instance where a certain workload can be instantiated. In the next step, service orchestration, supported optionally by a multi-cloud module, calls the cloud APIs to deploy VNFs. Finally, controllers apply the configuration on different VNFs in order to activate a complete customer service. Those are the essential ONAP capabilities available to implement common service fulfillment automation tasks. ONAP also provides several capabilities in the Automated Network Operations area, also known as the Service Assurance area in the ETOM terminology. Essentially, a prerequisite to execute service operations actions is an existing service instance or a set of instances. Operations are performed against VNFs, resources, included in the service instances. It is important to understand that a single VNF type, that is to say a VDNS or a VFW, could be used in different services in a different context, and as a consequence, different monitoring events might be relevant to be evaluated. Service assurance operations are based on the monitoring events generated by VNFs in a format compatible with ONAP collectors. ONAP provides at least 3 important capabilities, which can be used to assure continuous service operations. First of all, event data collection. Thanks to collector capabilities, events emitted by VNFs could be collected and distributed within ONAP to several applications, which are able to analyze the events. Analytics applications provide capabilities to evaluate events, faults, performance counters, heartbeat events, and so on. Out of the box, ONAP provides two applications, HOMES and TCA. HOMES can be used for alarm correlation. For example, the relation between a VM down to an affected VNFC, to an affected VNF, to an affected cloud service, to a server down. Threshold crossing application, TCA, can be used to trigger actions based on the evaluation of measurements versus predefined thresholds. Policy. Policy processing capabilities of ONAP allow one to define rules, conditions, and restrictions related to actions executed on VNFs. There is a broad range of actions which can be executed, starting from VNF reconfiguration through scaling actions and self-healing behaviors. Policy helps to define as well when such actions could be executed. For example, during hardware maintenance, it is normal that certain alarms will be raised. In case of limited compute resources, a priority between VNFs needs to be enforced. Of course, specific actions are executed on VNF instances through a number of controllers, which target different aspects of VNF operations and offer different mechanisms, protocols. Finally, after the events are collected and analyzed. If policies allow a closed-loop action to happen, the VNF configuration and its infrastructure topology details are updated. Continuous execution of closed-loop activities enables 24/7 service assurance through automation. Now, let's look at the scope of ONAP. The scope of ONAP in the context of CSP is pretty broad and mainly covers functions supporting service fulfillment and service assurance business process groups, as defined in ETOM. The service definition starts with design, where ONAP supports customer service modeling, as well as network service modeling. Service design is followed by service deployment, which is covered by ONAP. Primarily, telco services are concerned. As ONAP aligns with TSCA and targets full alignment with ETSI NFV standards, primarily telco services and applications VNF orchestration are in focus. A specific activity in NFV environments is the setup of virtual links, modeled entities, within a VNF between different VNFCs, as well as between VNFs within a network service. This is a specific activity visible when operating on NFV environments, while standard IT-based environments usually offer much simpler networking and much less capabilities. ONAP is able to model and deploy virtual links using the open-source SDN controller. A unique capability offered by ONAP, in contrast to other open-source orchestration platforms, is the service VNF configuration capability. ONAP offers several configuration mechanisms that can be used in initial service deployments, as well as in closed loops. Service instance placing optimization is as well definitely in the scope of ONAP. Due to the fact that the majority of network services in use come with strict QoS requirements, throughput, latency, jitter, the placing optimization functionality is crucial to make sure that services are delivered with the requested quality. ONAP has dedicated modules that can be used to calculate optimal cloud regions to deploy specific service instances. Finally, a policy engine is essential to deal with prioritization of activities and evaluations of rules, conditions, and restrictions related with service instance creation, as well as service operations actions. From the perspective of limited compute capacity, ONAP's scope covers closed loops operating in the telco services space. At this moment, closed loops are associated with VNFs, resources, running as part of a service. And there is only little to none interoperability between closed loops operating at different levels of services. Such interoperation is currently outside of the ONAP scope, and several organizations are evaluating solutions for closed-loop interoperability. One of the most important functions in the scope of ONAP is service modeling. Service modeling allows using ONAP, which is only a platform that can be used for automation, to have a role in a specific telco operations domain, like core, radio access, fixed, and access. The model-driven approach behind ONAP allows the platform to support a bunch of different services built using different VNFs, which serve a service building block. Many VNFs are bound to a specific telco domain, core or RAN, for example. But there is a huge amount of VNFs that can be reused in many services. Some examples are vDNS, VFW, and vDHCP. Service modeling allows operators to bring new use cases on ONAP and gradually support more and more technical domains, using the same platform software, such as ONAP, using the same deployment and management mechanisms. Today, several reference services are available in ONAP out of the box, like VoLTE, vCPE, belonging to the fixed networks domain, and many new reference services are in preparation, like 5G vRAN services. Operators are still able to create new services as needed, using dedicated or reusable VNFs. Those could be based on reference services or completely new ones. Reference services and possibility to reuse certain VNF models in new services effectively reduces the time needed to design and expose new services to customers. After modeling activities, operators are ready for deployments. Here, it's important to remind that cloud instance region deployments are clearly outside of ONAP's scope. Still, within ONAP's scope are the capabilities to support different cloud and containerization environments. It is already possible to select an optimal cloud region to deploy a complete or relevant part of a service VNF based on a number of factors. Those can include restrictions like certain cloud types, available cloud compute storage capacity to host VNFs, maximum network latency to access a cloud instance, or between cloud regions. The optimization framework used here is flexible enough to be extended with additional factors, like cost of operation. Today, ONAP mainly supports OpenStack clouds, and a number of OpenStack distribution vendors have demonstrated working integrations with ONAP. Public clouds like Azure are supported today, ONAP Casablanca release, in a sense that there is a necessary adapter which could be used for deployments. Still, it is important to understand that currently, the public clouds are not offering the configuration flexibility needed for certain VNFs, especially in the network area. Evolutionary, it might be possible that the common VNF design will be simplified and the public cloud network flexibility will be improved, resulting in a possibility to leverage public cloud benefits in the core telco industry. Finally, ONAP is currently being extended to fully support cloud-native network functions, which are targeting fully containerized deployments. In this area, starting with Casablanca release, ONAP brings initial support for Kubernetes environments. In order to fully leverage such environments, additional work on containerized network functions is needed and already planned for the ONAP Dublin release. Service operations is another important area in the scope of ONAP. Essentially, ONAP provides a mechanism of data collection and distribution, capabilities to onboard certain analytics applications, and to define policies. Let's have a closer look at the capabilities brought by ONAP. Event collection. ONAP defines a number of interfaces that can be used to send monitoring events to ONAP. Virtual network functions need to shape those events according to schemas defined by the ONAP DCAE project. Essentially, the format definition for those events is currently in the scope of ONAP. Analytics. Within the analytics space, first of all, ONAP defines a mechanism for bringing analytics applications to the ONAP DCAE environment and connecting them to event data sources and policy. Out of the box, the Casablanca release comes with two analytics applications: HOMES for fault management and TCA for performance monitoring. Although those applications can be used in closed loops, their functionality is limited compared to full-fledged element management systems, EMS, available on the market. It is important to understand that in this analytics space, the ONAP's scope is to provide this mechanism, which allows different applications, specific to a domain, crafted to a use case, customized, etc., to be onboarded and used as part of a closed loop. The ONAP scope is not to replace an EMS system here, but rather to provide a platform that can be used to build an EMS-like functionality. Policy. In order to implement closed-loop mechanisms, ONAP provides a policy capability. The ONAP scope here is to provide an integrated business rules management system, which can be used to provision different rules related to many areas of network operation. Additionally, those rules could be dynamically loaded in the system and applied to running service instances. Still, the scope here is to provide a rule engine rather than specific rules that can be applied for certain services out of the box. Although the scope of ONAP is really broad, there are certain CSP operation areas which are outside of it. IT application orchestration. This aspect is covered by many platforms available on the market today, which can be used. Still, ONAP is targeted to support high-performance, low-latency telco applications, which come with specific requirements. Operating IT applications with ONAP might be too complex compared to the expected benefits. BSS CRM applications. Business support systems and customer relationship management functionalities are covered by specific systems. ONAP doesn't target to replace the existing BSS landscape, and the scope doesn't cover applications exposed to CSP agents or CSP service subscribers. IoT management. ONAP is not planned to serve a full-fledged IoT platform, which supports massive data collection and analytics needed in the IoT use cases. Still, ONAP is able to deploy and assure the connectivity needed by IoT applications. There are some activities around the support of 5G and network slicing. Full-fledged inventory. Although ONAP comes with a built-in inventory subsystem called Active and Available Inventory, A and AI, its target is to store data relevant to ONAP and services, which are hosted on ONAP. There is currently no intention to host information such as guarantee, license utilization support contract details associated with VNFs of PNFs managed with ONAP. Still, certain operators integrate the full-fledged inventory systems with ONAP, especially in the case of PNF management. Cloud deployments and cloud region operations. As of ONAP Casablanca release, there is no intention to deploy cloud instances, regions, as part of the ONAP scope. Such environments need to be deployed with external capabilities and managed by specialized operation teams. Still, the cloud API details need to be configured on ONAP to allow for deployments in those cloud instances regions. SDN infrastructure setup. ONAP is able to leverage SDN capabilities when building networks to interconnect VNFs, provide intra-VNF connectivity and external connectivity. Still, it is not in the scope of ONAP to build the infrastructure needed for the SDN to work. Such an infrastructure needs to be built by specialized personnel and made available to be used with relevant ONAP modules. The purpose of ONAP is to provide capabilities for real-time service fulfillment, as well as continuous service operations. Simplifying and automating these tasks is crucial in our today's always-on world, with growing importance of large web social media companies. The scope of ONAP covers design, deployment, and assurance of services used in the communication service providers industry. Within service modeling, ONAP provides a service design capability, which allows one to automate deployments and operations of different network areas aspects. Within service deployments, ONAP provides the capability to interact with different cloud platforms, private, public, soon containerized environments, and coordinate deployments in different cloud regions. In the service operations area, ONAP defines closed-loop mechanisms and allows domain service-specific analytics application onboarding. You can now close this window and move on to the next module.